Sorry, Jian, I cannot hear you. So we were able, I was able to hear you earlier, but somehow now.
Can you hear me now or not?
I can hear you now, yes.
Okay, yeah. Thank you for the opportunity. To invite me to talk here. So, hello everyone. I'll talk about my recent work with my supervisor friend. And the title is about foliated asymptotically safe gravity in the foliation approach. So the main idea of this work is that we use the fluctuation approach to compute the RG flows on the foliated spacetime. So here is the outline of my talk. First, I will give an introduction of our work, where I will give the motivation that why we want to do the fluctuation computation on the foliated spacetime. On the next, I will briefly review the ADM formalism, since some of you may not be familiar with this formalism. After this, I also review the fluctuation approach computation for the FRG. First, I'll briefly review the fluctuation computation for the covariant case. On the other hand, I will adapt the formalism to the ADM case where the spacetime is foliated. After the background knowledge, I'll then introduce our setup on the computation for the RG flow of graviton two-point functions. The computation will be carried out for two systems. The first system is the foliated Einstein-Hilbert truncation, where we consider the Einstein-Hilbert action in the ADM form. The second system is the Lorentz symmetry violation system. In the second system, will include the Lorentz symmetry breaking couplings on the after this, finally, I will give a summary on the outlook of our research. Okay. First, let me start with the introduction. Yes, we all know that most works in asymptotic safety are carried out on Euclidean spacetime. Then, the Lorentzian asymptotic safety program is an open question in this field. So now there are several methods to construct the Lorentz asymptotic safety. So this method includes the recently developed graviton spatial function approach, and also the algebraic quantum field theory approach to the Wetterich equation, and also the functional renormalization group in ADM formulated. In this talk, we'll focus on the third method, where we use the functional renormalization group in ADM formulation to compute the RG flow. So now let me briefly explain this method with FRG in ADM fields. First, in the ADM formalism, the physical degrees of freedom are not encoded in the metric. Instead, they are encoded in the ADM fields here, the last function, the shift vector on the spatial metric on the spatial hypersurface. So this ADM decomposition also introduced preferred time direction in the space-time on the this preferred time direction also foliated the space-time. So in this ADM setup, the transition from the Euclidean to Lorentz space-time can be easily done by the transformation of the left function. If we do this transformation, then the space-time will become the one with the Lorentz signature. Similarly, like we can also apply this transformation on the effective edge action, which is also a function of the ADM fields. Like under this transformation of the left function, we could also write down the effective edge action from the Euclidean ones easily by this transformation. So until now, like both the Euclidean and the Lorentzian effective edge action can be like solved by the Wetterich equation on the there have been some work on these directions to compute the RG flow for both Lorentz and the Euclidean effective edge action on the foliated spacetime. We should note that before this work, like most of work in this direction are done at the level of background computations. So in this talk, like we'll only consider like Euclidean spacetime in the ADM formulate. Like we will not do the Lorentz case in this talk. The Lorentz situation will be considered in our future work. So this talk could be regarded as an intermediate step towards the Lorentz case. In addition, like we will go beyond the background computation on the carry out the fluctuation computation of FRG in the ADM field. So the reason why we want to carry out the fluctuation computation is that like this fluctuation approach allows us to investigate the global structure of the RG flows. Maybe we need to recall the background computation. Usually in the background computation, we need to employ the hit kernel to evaluate the trace on the right-hand side of the Wetterich equation. Then, like in the UV, we need to employ the early time expansion for the hit kernel, but in the infrared, we need the late time expansion. But in the the things are different in the fluctuation computation. Since in the fluctuation computation, we can just use a like flat background, so the trace evaluation can be converted into the integral of the momentum. Then like we can deal with the UV and the IR component in like at the same time. Then specifically in this work, like we will compute the RG flows of the graviton 2-point functions. That means like we only project onto the 2-point function. Here, graviton means that we use the York decomposition for the fluctuation of the spatial metric on the graviton is referred to the transverse traceless components of the spatial metric fluctuation. Okay, so now let me briefly review the ADM formula. So the basic idea of ADM decomposition could be given as the flow chart in the left panel. So first, we can introduce a global time function on the space-time M on the this global function this global time function introduced like a family of spatial hypersurfaces, like in the spacetime on the. Then this spatial hypersurface just foliate the spacetime on the. Oh, sorry. Yeah. Then like we can express the full metric, the four-dimensional metric in the spacetime in terms of the geometric quantities norm or tangent to this spatial hypersurface. So yeah, we can illustrate this idea by this very nice figure from this paper. So here we have two spatial hypersurface on the T here is the here T is the vector generated by the global time function. And we can see that this vector can be like become the this vector can be given in terms of the components normal to the surface and the tangent to the surface. Yeah, similarly, we can also do this decomposition for the full metric. So here is the result. The full metric could be given by the last function, the shift vector, tangent to the hypersurface, and also a spatial metric on the hypersurface. Then after we have this 3+1 decomposition of the metric, then we can write down the action of the theory. Like in this talk, we will just focus on the theory with at most two derivatives, which can be given in this way. Here K is the extrinsic curvature, and R3 is the internal curvature defined on the spatial hypersurface. We noticed that in addition to the Newton coupling on the cosmological constant, we have another two couplings, alpha 1 and alpha 2. Then there are three very interesting cases associated with different values of alpha. For example, we can set like alpha 1 and alpha 2 to be 1 by hand. And then in this case, we just recover the Einstein-Hilbert action in the ADM form. On the other hand, like we can also identify alpha 1 with alpha 2, and we regard them as running couplings. And this case corresponds to the relative scaling between the spatial and the temporal fundamental length in the CDT program. Since in the CDT, like the space-time is given by the blocks of the by the fundamental blocks. So the blocks in the time direction and in the spatial direction could have different size. So this coupling just gives the relative scaling between those two directions. Another one is that we can also set alpha 1 to be 1 and regard alpha 2 to be a running coupling. In fact, this case is exactly the same as the infrared component of the Harari gravity. So in this work, like we treat the two derivative action, this one, as the seed action to generate the tensor structure to expand the two-point function, also to project our flows. So at this stage, like we will not face alpha 1 and alpha 2. We still treat them as like free parameters. So that means the resulting theory may break the Lorentz symmetry. So since we could only recover the Einstein-Hilbert action with them set to be 1. So we'll come to this part later. So Now, let me also explain the fluctuation approach like in this slide. So we first start with the fluctuation computation like in the current form. Like here I just give like a very rough picture of that. Like if you want to know more details, you can find in the very nice review by Yang on the manual. So yeah, let's start with the Einstein-Hilbert action. So first, we can do the vortices function for this Einstein-Hilbert action. Then the first term is the background quantities, like they correspond to the zero order of the fluctuation. Then we can give the first order fluctuation. We can also give the second order fluctuation. Which is given here on the other higher order terms. Like for the background computation, in fact, like they are correspond to like evaluating the RG flows for the countings appearing in the zero order of the fluctuation. Like the beta function or the RG flows of this background countings are gotten by projecting onto the background quantities like the background curvature on the background spacetime volume. Here we denote the background coupling with the index 0, means that they are for background. Here, for the fluctuation computations, like in fact, in this approach, like we are evaluating the RG flows for the correlation functions of the fluctuations. Like gamma 2, gamma 3 on the other higher order correlation functions. Usually, the RG flows of the correlation function in order n could be given by taking functional derivatives on both sides of the Wetterich equation. We will illustrate this technical issue by the 2-point functions in Einstein-Hilbert truncation. Like for the current Einstein-Hilbert truncation, the 2-point function can be given in this simple form. Here we only consider the TT components on the then the flow. Oh, sorry. Then the flow of this 2-point function can be obtained by taking second order function derivative of the original Wetterich equation, which is given as this equation on the. Now, if we want to extract the RG flow or the base function of the Newton coupling, we need to project onto the terms linear in p square on both sides of this equation. Then if we set if we only care about the term linear in p square, we will just get this coefficient. Then we will read the beta function of G2. Similarly, if we want to get the flows for the cosmological constant, we can simply simply set P0 to be 0. Then we could read the RG flow for this coupling. Here we use the index 2 to indicate that like they are the couplings appearing in the 2-point function. So in fact, or in principle, they should be different couplings from the ones in the background computation or background quantities. Okay. After we have the general algorithm, now we can go to the foliated case, like for our two derivative action in the ADM form, which can be given in this formula. We could get the 2-point functions for the for the transverse traceless components in this way. Now we notice that, like in general, these 2-point functions are non-relativistic, since here we have the coupling alpha 1, and alpha 1 could be a running coupling. It could be any number. If it is not 1, then the theory will not be Lorentzian invariant. So now we can consider two cases. Like for the first case, it corresponds to the general case where alpha 1 is not 1, it's a running coupling. Then we can extract the flow of alpha 1 and also other couplings from the tensor structure of time component of the external momentum and the spatial component of the external momentum, and also the tensor structure independence of the external momentum. Then for the second case, like we can set alpha 1 to be 1, then we just go to the covariant 2-point case. Now, like we have two couplings, like the Newton coupling and the cosmological constant. But we have 3 tensor structures. Then that means, like, we have 2 different projection methods. Like for example, like we can extract the flow of those 2 couplings from the spatial momentum part and also the part independent of the external momentum. So we call this projection method as the p-vector projection. We can also do the p0 projection, where we extract the RG flow of Newton coupling from the time components of the 2-point function. In fact, like if we can recover exactly the Lorentz symmetry for our theory, in fact, these 2 projection methods should give exactly the same results. So it doesn't matter which projection method we use, but in practice, we'll show that, like, it's very hard to recover the Lorentz symmetry exactly. So like the result from those 2 projections may be slightly different. Now let me show that. So here is our two derivative action in ADM form. Like first, let's consider the 2-point functions. First, we notice that even we set alpha 1 and alpha 2 to be 1, then for some components of the 2-point function, like they are still non-relativistic. For example, if we do the computation for the vector modes in the Euclidean decomposition, we found that this component of the 2-point function only depend on the spatial momentum. So that means this mode doesn't propagate. So it's quite a problem. So this question can be fixed by introduce the gauge phase term, like, which is quadratic in the fluctuation. Since this gauge phasing term is quadratic in fluctuation, so it could contribute to the 2-point function. And if we can choose the gauge parameter, probably then the resulting gauge fixed 2-point function will be relativistic for the case with alpha 1 on alpha 2 set to be 1. Yeah, but the question is that here the gauge fixing method, only contains the gauge fixing term qualitative in the fluctuation, so it will not contribute to the higher order functions. So if we look at the higher order ones, for example, like the 4-point functions, we will see that even for this case, like where we set those two coordinates to be 1, we will find that the 4-point functions are still like non-relativistic. So that means like if we are still working with this gauge fixing method, then this higher order vortices will like enter the right hand side of the Wetterich equation, and then it will also enter the flows of the coordinates on the, since this part is non-relativistic, so the result RG flows may be also non-relativistic. Yeah, that means indeed p vector on the p0 projections could lead to different results. So at this stage, one may think that we can repeat this idea like by introducing higher order gauge fixing term, like in the theory, to make all the higher order functions to be relativistic. But at technical level, it's very hard to realize that, since like usually the 4-point functions contain maybe several hundred or maybe 1,000 terms. I mean, then that means like we need to determine maybe several hundred gauge parameters. So it's almost impossible to realize that like in the actual computation. So in this talk, we will still work with the gauge fixing term quality in the fluctuation. Yeah, but anyway, like as we will show later, like even these two projection method will lead to slightly different result, but they could still give some like qualitatively similar result on the structures. So so that means like this gauge fixing method is still like a good approximation to do the computation, I think. Okay, let's. Sorry. Okay, so let's go to our setup. So in this work, we will work with the following effective edge reaction. So for the gravitational part, like we approximate the effective edge reaction with our two derivative actions. Yeah, here we still have two running coupling alpha 1 and alpha 2. And the gauge fixing term are like corrected in the fluctuations, and the corresponding ghost term can be obtained from the standard Foliated method. So we will not give the details here. So in this talk, we will project the flow onto the 2-point function of the transverse traceless components of the spatial metric fluctuation. Like the 2-point function can be given in this way. So finally, we need to specify the regulator part. Now, since like the 2-point function in general like are non-relativistic, we can further look at the trace part of the 2-point function. We can see that it comes with more ugly form. So in order to implement the regularization, like we define the non-relativistic form momentum in this way. Here we introduce like a parameter alpha. Here alpha could be any number. Then, like with this notation, the regularization can be given by the following replacement. So the essential part is that the regulator only depends on the covariant for momentum. So where we set alpha to be 1. That means like, if we set all the coupling alpha 1 and alpha 2 to be 1, like in the effective edge reaction, then this this regularization will just recover the type 1 regularization. And in this work, like we work with the optimized cutoff function for the regulator function. Yeah. So now, we already give, like in the previous slide, like the flow of this 2-point function can be given in terms of the 3-point function and the 4-point functions. Yeah, and also the propagator. Here the propagator is the inverse of the regular 2-point function. And in our computation, the 3-point and the 4-point vortices are generated by the two derivative action in ADM form and also the corresponding Gaussian parts. Yeah, in addition, like in the 3-point and the 4-point functions, they also have their own like avatars for the coupling G3 and G4, also lambda 3, lambda 4, and so on. Like in order to close the system, like in this talk, like we will identify like G3 and G4 with G2. So that's our setup. And with this setup, like we'll compute like 2 different systems. Like the first system is we call it like a foliated Einstein-Hilbert truncation, which means we set alpha 1 and alpha 2 to be 1. The effective edge action just recover the Einstein-Hilbert action in ADM form. The second case is the Lorentz symmetry breaking case. Yeah, where we including the Lorentz symmetry breaking coupling alpha 1 and alpha 2. So now let's go to the first case, the foliated Einstein-Hilbert truncation. Then in this case, since we set alpha 1 and alpha 2 to be 1 by hand, then like the 2-point function can be given in this relativistic form. As we said before, the running of this Newton coupling can be extracted from either the spatial momentum part or the time component of the momentum or the spatial part of the external momentum. So that will lead to different projection rules. But in fact, like in the end, we found that our beta function can be given in the following form. For the beta function of G is almost the same as the background computation. Yeah, since in this case we didn't consider the 3-point. The Newton coupling from the 3-point vortices. So so in that sense, like you can see the Newton coupling is not dynamically still. It's not disentangled with the anonymous dimension of graviton. And for the bit function of the cosmological constant, it depends on some like on some like polynomials of the of the cosmological constant. Here, this form of the basic function holds for both projection. Like for different projection, like for P projection, P0 projection or P vector projection, they just lead to different form of B1 on the B2 function. So here we give the plot of those two functions with different projection. Yeah, we can look at the left one. Like for the P0, for the B1 function, the P0 projection on the P vector projection could give like the same shape of the function. So that means these two projection methods lead to like qualitatively similar RG flows. So yeah, we can infer that like the result, you can say flow diagrams or the phase point structure should also be qualitatively similar to each other, right? So now with our base function, we can solve the phase points. We just give the result here. So for the P0 projection, yeah, we can find a Gaussian phase point on the several non-Gaussian phase point. Here we only keep the one with positive Newton coupling. First, for the Gaussian one, like we can easily verify from these two functions. If we set G on lambda to be 0, yeah, those two functions just vanish. So under their scaling property, also agree with like the classical math dimension of the coupling. For the non-Gaussian fixed points, we found that like two different projections indeed lead to like slight different values for the phase point, but they share the same qualitative structure. Like for both of them, like the value of Newton coupling is around like 1. The value of the cosmological constant is around minus 0.1. So in addition, both of those two phase points come with like two relevant directions. This feature, yeah, in fact, agree with other computation. Like for comparison, we also give the background computation of the ADM from, yeah, where they also have two two relevant directions. Yeah, in addition, we also give the fluctuation computation in the current case. Yeah, where they have already included the Newton coupling from the 3-point function on the. Here they also have like two relative directions. Yeah, here we may want to stress that, like, in fact, for those different blocks, like the background computation or current case or the foliated case, in fact, like we are doing the computation for different couplings. So in principle, we cannot directly compare those results. Yeah, but all of those results together just indicate that, like, no matter which no matter which computation method we use, or no matter which structure of spacetime we use, like the theory with two couplings should always be like if we complete on the asymptotically safe, and they always come with like two relevant directions. Next, we will give our flow diagrams, like for both projections, like from the here is the UV fixed point, and here is the Gaussian fixed point. And from the flow diagram, we can see that like both projection lead to similar structure, right? And also, like in addition, we could identify infrared fixed point around like J star to be 0 and lambda star to be around 1/2. This one is also reported in the fluctuation computation in the current case. Since since the bit function are degenerate around this line, maybe we can quickly go back to the bit function. Like we can see from bit lambda, if lambda is 1/2, this one will diverge. So that's why we didn't get this phase point in the previous calculation. Since the bit function degenerate in this point, so the existence of this infrared phase point need to be confirmed by analyzing the scaling property of the RG flows at this point. So in this picture, we pick, I think, 5 RG flows, and they are labeled by different colors. And we do the numerical analysis for those RG flows, and the behavior of the couplings along those RG flows are given by those two figures. We can see that, for the cosmological constant, it approached the infrared phase point in infinite RG time. So so we can also do the analyze which gives that the scaling around this phase point for the cosmological constant is going like this way. So in this sense, we can say that all the RG flows in this region process are good limits. So this point can serve as infrared phase point of the theory. So in addition, since the phase point value of the dimensionless cosmological constant is finite, it's just around half. So that means the dimension for cosmological constant in the infrared should go to 0, since we have k squared, right? That means all the RG flows in this region bounded by the black thick lines come with 0 renormalized mass. That's different from other RG flows. For the RG trajectory in this region, they go to the minus infinity. So in that sense, the renormalized mass in the infrared may not be 0. Okay, so now maybe at this stage we should give a short discussion or summary on this subsystem. So first, we could identify. Oh, sorry. Let me move this part. First, we identify a phase point around G, around 1 on the minus 0.1 for both projection, and we also obtain the flow diagrams where the infrared is also complete. So from the phase point structure on the flow diagram, we see that, indeed, those two projection methods lead to qualitatively similar results. So that means our gauge phasing method with quadratic fluctuation can be regarded as good approximation. But the results are still not the same, not exactly the same. So there are some possibilities to break the Lorentz symmetry in our computation. Yeah, the first element is the one we already mentioned. Yeah, is that where like the 3 on the 4-point vortices are non-relativistic. This might be fixed by the higher order gauge phase term, but in practice it's hard to do. Maybe we will go to this in the future, maybe not. Yeah, another possibility is that like the regulator term could also break the Lorentz symmetry or full spacetime diffeomorphism. Yeah, the reason is that usually the regulator is corrected in the fluctuation. Yeah, but the ADM decomposition is usually nonlinear. That means like a regulator term in the current spacetime, which is corrected in the fluctuation after the ADM transformation, may be nonlinear, or so that so that term would also break the Lorentz symmetry. If we want to investigate this effect, like we need to consider the modified word identity or other symmetry identities. Yeah, we will not consider this either in this talk. And in addition, we also identify inference phase point around this place. And as we mentioned before, this inference phase point is already found like in the fluctuation approach with current sighting. I think this is the first time to have this inference phase point in the foliated spacetime, I think. Okay, now finally, let's go to the system, including Lorentz symmetry breaking coupling. So in this case, alpha 1 and alpha 2 should be regarded as running couplings. Then the graviton two-point functions can be given in this form, and we can say that like for the TT components, like we don't have the coupling alpha 2 here. So if we want to solve the system, we must make some approximations for alpha 2. If we just stay in this projection, in fact, like in principle, the running of alpha 2 can be extracted from the two-point function of other two-point function. Like, for example, it can be extracted from the trace part of the two-point function. Yeah, but we will not consider that like in this talk. So in this talk, we only consider two approximations where we set alpha 1 to be 1 and where we identify alpha 2 to be alpha 1. Then the flow of those three couplings can be extracted from three tensor structures. Here we give the non-Gaussian phase point we found from the RG flow. Oh, sorry. From the first system where we set the parameter alpha 2 to be 1, we found a phase point with alpha 1 very close to 1. Yeah, that means this phase point is very close to the hypersurface, which preserve the full diffeomorphism symmetry. But for the case where alpha 2 is identified with alpha 1, we found that this phase point is shifted away from this hypersurface. So that means here the Lorentz symmetry breaking effect may play a very strong, very important role, or may have a very strong impact on the system. So It may need to investigate in the future. Anyway, for both of the systems, we could identify like three relevant directions. Now, let's consider the inference part by analyzing the Gaussian phase points. So around the Gaussian phase point, where GK on lambda k is 0, we can expand the RG flow, the beta functions, and they can be given the following form, and we can see that if we set G on lambda to be 0, those three beta function would vanish trivially. So that means like there is a family of generalized Gaussian phase point. In this family, G on lambda must to be 1 and alpha 1 to be can be any value on the corresponding critical exponents are the same as the previous case. We also know that notice that this family of Gaussian phase points is also reported, like in the previous background on the computation, which also includes non-relativistic truncations. So here we may infer that like this feature of like of a family of Gaussian phase points maybe are like a general feature of the non-relativistic theories. So, okay, finally, let me go to my conclusion on the outlook. So, in this talk, like in our work, we compute the RG flows for the two-point functions in two different systems in the foliated Einstein-Hilbert system. We identify the non-Gaussian phase point, and we also found additional infrared phase point. And they could serve as the UV and the infrared completion of the theory. And I think this is also the first time to identify this infrared phase point, like in the foliated spacetime. And we also did the computation for the system, include the non-relativistic coupling. And for this system, we could also identify the non-Gaussian phase point as the UV completion of the theory. And we also found that like a family of Gaussian phase points, which agree with previous background computation. So the outlook for the future research could be given as following two directions. First, we noticed that the Lorentz inverse is not recovered exactly, since the phase point value are still different. So, we may need to solve this in the future. Maybe we need to include the higher order gauge phase method, or we may need to consider modified word identity, or we may need to include the full momentum dependence of the two-point function. A lot of things to improve this. On the other hand, like our computation now is done on Euclidean spacetime, so it's quite natural to do the computation on Lorentz spectrum. And the Lorentz computation can be easily done by replacing the regulator with a function which only depends on the spatial momentum. Okay, thank you. That's all of my talk. Thank you for your attention.
Yeah, thanks a lot, Jian, for the very nice talk.
Yeah, thank you.